So, hello everybody, and thank you very much for attending this lecture this afternoon. So, the whole lecture will be recorded. I will present a short bio first, and then Veerle will go on with the InterPore distinguished lecture, and then we will have a few minutes at the end for questions. So people who would like to ask questions can either post them, or if they wish to ask them, they're very welcome to let me know in the chat, and I will give them permission to talk. The whole thing of muting all you was because I just wanted to avoid having further noise. So we are delighted having Professor Veerle today in this virtual talk. The very first idea was to have Veerle here in Heriot-Watt in a face-to-face meeting back in May 2020, but then due to several complexities related to the COVID pandemic, we decided to postpone the talk and then finally to have it in a virtual form just before the end of 2020. So, Professor Veerle Cnudde received a PhD in geology in 2005 from Ghent University in Belgium, where she has been a research professor since 2010. She is a team leader of Progress team, the Pore-scale Processes and Geomaterials Research Group at the Department of Geology at University of Ghent, and it's one of the coordinators of the Ghent University Expertise Centre for X-Ray Tomography. Veerle was one of the co-founders of the UGCT spin-off company Inside Matters, which later merged with the spin-off company XRE, now is part of TESCAN. Veerle specializes in non-destructive imaging of geomaterials and has a strong expertise in real-time imaging of processes in the pore space. Research projects which she has initiated are strongly linked to weathering and fluid flow processes of porous sedimentary rocks, as well as conservation of building stones, so a wide range of applications. Professor Veerle Cnudde has published more than 100 peer-reviewed journal articles. She is currently the chair of the Proposal Review Committee of the TOMCAT beamline at the Swiss Light Source. She is one of the co-founders of the InterPore BENELUX and an elected council member of the InterPore. In 2019, she became part-time full professor at the Environmental Hydrogeology group at Utrecht University in the field of porous media imaging techniques. And we are very happy to have you here with us, Veerle, to talk to us about pore-scale processes in geomaterials.
Thank you very much, and thank you for giving me the opportunity to present some of the work we have been doing at Ghent University. So I'll share my screen, and then we can start. Okay, can you see this? Yeah?
Yep.
Okay, unraveling pore-scale processes in geomaterials. I could talk about many things just looking at the title, but in my talk this afternoon, I will talk about weathering of rocks as an example of those processes. Because if you just look at the phenomenon like weathering of rocks, this is a combination of different aspects. It's physical, chemical, and biological weathering. And if one wants to understand what's happening there, people try to do many things in lab environment to be able to understand what's happening and also to be able to predict what is happening or what will happen with rock. And so people typically go to a quarry or a monument. They first do macroscopical observations of what they can see. Then they take subsamples, they go to the lab, and then they start to do a series of tests. This can be identification tests of the rock itself to characterize this using different techniques like optical microscopy and scanning electron microscopy to identify the rock itself by identifying the minerals that are present. To do also some tests related to how the stone behaves, some physical tests to know how the compressive strength is, the tensile strength, how the pore size distribution are by intruding mercury intrusion porosimetry, to do some tests related to capillary water uptake, drying rate, because weathering is an important factor related to rock weathering is related to fluid flow behavior. So, and if you're studying fluid flow, you want to know how fluids are moving in the system. The rock 3D characteristics. So people can do many things with those samples in lab, and they can even also do some durability tests in order to predict how a rock will be sensitive, for instance, to freeze-thaw weathering as an example. However, in reality, what you measure in lab related to durability does not always reflect, or often does not reflect, what we see in reality. Lab results and reality are often different. And this has to do with several aspects, but important things are that in reality you have the combination of different processes, while in lab you're often studying one. And then in reality also the environmental conditions are often different, because if you do experiments related to weathering in lab, you want to make these processes go faster in order to have an idea what will happen with the rock over 10 years. However, if you speed up the process and you change the temperature and relative humidity conditions, for instance, you're also triggering other processes. And so this makes it very difficult to link this. Also, in reality, we are dealing not always with fully saturated rocks, which they sometimes examine in lab, but often it's semi-saturated rocks. And so you have a lot of differences between reality and what's happening in lab. And if we really want to understand what's happening on the rocks, we need to have insights in the microstructure in 3D, also the 3D chemical composition of the rocks that we are examining, and then also in the 3D dynamical processes on the pore scale, because this is the key to understand what's happening on the macro scale. And so the way to do this is using techniques which allows you to do integrated experiments, like combining high resolution so that you can see on the pore scale, but also techniques that allow you to visualize dynamic processes, that allows you to see what's really happening inside a rock when it is under certain circumstances. And use this information then to be able to understand and potentially predict macroscopical behavior of a rock in a better way. So the way we do this is using X-rays, and they were discovered by Röntgen, for which he got the Nobel Prize. And the power of X-rays is that, unlike visible light, they can penetrate matter. And so therefore they're ideally suited for internal inspection of objects, which is also done in medicine, for instance, or at the airport. They use X-rays to look inside a body of a patient or your luggage. So X-rays are ideal to look inside a material. What do you measure there when using X-rays? When you use an X-ray detector is what you see there in an X-ray radiograph depends on the density and the average atomic number of your materials in question. So if we want to look inside the geological material, we need to have sometimes contrast to see, for instance, between a pore and a calcite grain. That is no problem. But if you want to see different behavior between different grains, you need to have also contrast. contrast. So this is already important when using X-rays. And so basically what you need in order to perform X-ray radiography is you need an X-ray source and a detector, and what you measure on your detector is depending on the interaction of your X-rays with your sample. And so this allows you to do many things already, but was not enough to come to 3D information. So in the late 60s, early 70s, Cormack and Hounsfield built a first X-ray CT scanner, or computed actual tomography scanner. And this system allows you to go for 3D scanning of your material. And in a medical scanner, maybe some of you have worked with medical scanners to study their cores, for instance. In a medical scanner, it's the core that lays stable, and the source and the detector are rotating around your core. And so also with the development of CAT scanners or CT scanners, in the beginning it was mainly used for medical diagnostic imaging. However, it's from the end of the 70s that it started to be also applied in an industrial environment. And what is the difference between X-ray radiography and X-ray tomography? The only difference is that you take now a series of radiographs over your sample while rotating, or your sample, which is illustrated here, or by having a source and detector rotating around your sample, which is, for instance, the case with a medical scanner. And what you measure in your X-ray detector depends on the intensity that is coming from your X-ray source, the interaction from your X-rays reacting with your sample. And this interaction is depending on the average atomic number of your minerals composed in your sample, the density of what is inside your sample, and also the amount, the scale, the length that the X-rays have to penetrate through. So these things are all recorded in one radiograph, and by rotating your sample or rotating your source and detector around your sample, you get a series of radiographs which record all this information over different angles. And then the way the next step can be is, so the set of radiographs is the raw data. The raw data set of a CT scanner. And what we then do is often we use filter back projection. This is one of this is a software tool to come from the raw data to a real 3D image. And so the principle behind this is I explained this rather simple, but the idea is that if you look here on the left, you see an X-ray source, you see what is detected by the X-ray detector. In the middle, you have your sample. This information is recorded at one angle, but while rotating, you record this over different angles. And then with filter back projection, you back project this information in order to reconstruct the original image. You just apply a filter in order to have sharper edges. This is very simplified explained, but that is the main idea behind this. And so you can immediately see that the more projections you have, the higher the image quality will be, but also the longer it will take to do your scan. And so if you have a stack of radiographs, like here, of a limestone scanned at different angles, then by applying filter back projection, you can get one inside slide of it. But of course, we have the entire volume scanned. So as you can see, we have a radiograph of the entire rock sample. So we can do this for each slide, and we can combine this. And then it's just a matter of using a 3D rendering software in order to come to a 3D virtual image of the rock that you scanned, in this case, a French limestone. So this allows you to virtually cut open your stone in whatever direction you want. So if you now go back to our original question. Okay, you go on the field, you have an outcrop, and you take some stone samples. What can you do? So if you take samples in the order of centimeters, by like here, two sandstone samples of a Belgian rock, the Bris sandstone, where you can clearly see macroscopically some fractures present, and on the right, similar rock type, a sandstone, where you can see iron-rich layers. You can see them clearly visible. But if you put these kind of samples in a medical scanner, you will be able to clearly distinguish those fractures in 3D. So you can follow how the fracture pattern is internally structured, and you can also see how the layers are evolving, for instance, in function of depth inside your sample. And you see this because you have a contrast. The whiter, the brighter areas are the ones who have a higher average atomic number and are the iron-rich layers. One problem here, if you really want to understand the pore-scale processes, the resolution is not high enough. And you can see this if you take a small sample. This is a sample, for instance, of 1 centimeter diameter. If you scan this with a medical scanner, you will not be able to see the individual grains or pores. And this is because medical scanners typically have resolutions, depending on the system, in the order of 150, 200 micron. So if you want to visualize spores in the order of, or grains in the order of several micrometers, you need to have higher resolution. And that is why micro CT scanners were developed in order to go for higher detail. And one of the things is that when dealing with micro CT is that the smaller your average or your sample size is, the higher or the better the resolution will be. So if you have a sample, for instance, which is a core of 50 millimeter, it's no problem to reach a voxel size, and voxels is the 3D presentation of what you know as a pixel in 2D. A volume element. So the voxel size 13 micron, meaning 13 by 13 by 13 micrometer in size, allows you to see these kind of details. And the smaller your diameter of your sample is, the higher the voxel size, or well, the smaller your voxel size will be, so the higher the detail will be. And so it's no problem in order to come to resolutions or voxel sizes in the order of 1 to 2 micron in lab on a rock sample. But what is influencing the resolution? The resolution of a system, if you buy a system, they will say, okay, with this scanner we can reach a resolution of 1 micron. And the resolution is determined by the focal spot of your source, the average resolution of your detector, the distance between the source and the detector, and the distance between the source and your object. And these are important features, because it's not because in theory your scanner can reach a resolution up to 1 micron that for your sample with your specific demands, it will reach 1 micron. And I will explain it like this. For instance, if you are having an X-ray source, you can choose the energy, and depending on if your energy is higher for your X-ray source, your focal spot will also get larger. So if we are scanning in our facility light materials like plant materials, which are like almost cells with water and very light and average atomic numbers, then we can go for a small energy, a low energy. And by doing so, we will have also the sharpest and the smallest focal spot. While if we are scanning a rock or concrete, we need to have higher energy in order to penetrate the entire sample. And by having that, also depending on the sample size, but by having the need of going to a higher energy, your focal spot of your X-ray source will also become bigger. And by itself, it will already influence the resolution. So then it depends on the detector that you have in your system. In our facility, we have several detectors in order to cover different possibilities. And then, of course, some systems have the possibility where you can move the distance between the source and the detector, and others can't. In our facility, we can play with the distance between source and detector. And then the last thing is also the sample size. The smaller your sample will be, the closer you can put it to the X-ray source. And this is ideal because then your magnification will be the highest and it allows you to scan at the highest resolution. So it's trying to find the balance between having a bigger sample that you scan at a lower resolution, but having the entire volume in centimeter scale, or having examined a small sample during where you can scan it at a higher resolution. Another important thing to mention is that based on what I was saying related to filter back projection, is that during rotation we assume, or we hope, or this is our desire, that your entire setup and sample is not moving during rotation. So also there you have to have some stability. And so this is how an experimental CT scanner looks like. This is one of the scanners that we have in Ghent University. So UGCT stands for the Ghent University Centre of Tomography, and we are a core facility who provide access for academic and industrial collaborations. And so here you see two different X-ray sources. The micro X-ray tube, which goes for higher energy, but also has a bigger focal spot. And then the nano X-ray tube, who has a very tiny focal spot, but it's typically used for light material. Another important thing is that the smaller your focal spot, also the longer it will take to do a scan. So for certain things, if you want to do dynamic imaging, you sometimes would like to have a bigger focal spot to be able to have a higher signal compared to a smaller focal spot. And then we have rotation stays and a piezo in order to have our sample positioned in field of view during rotation. And then we have different detectors, in this case 2 detectors, the variant sensitive for high energy, so typically used for stone material, and then the photonic science, who is more sensitive for low energy, and therefore typically used for instance, plants and wood and animals like flies and spiders and things like that. This is all on, we have this combined with translation stages to have full flexibility. And as you can see, we can also move the position between the source and the detector. And this is all on an active vibration damping table. Also, our motor stage is air bearing, so that we do not have any movement during rotation. So we have built several scanners in the past, and our approach was to have also full flexibility, because if a new scanner if a new detector is available on the market, we invest in that new detector or in that new source in order to always have our systems up to date. And I will explain some of those systems more in detail later during my talk. But because of this 5 scanners, we have a wide variety of samples that we can scan. So different kind of samples, different kind of sizes. Of course, taking into account that depending on the sample size, you are also influencing the resolution. So if you want to study your rocks, you first need to go, or you first want to characterize them. And the first approach would be multi-scale 3D imaging. And if you normally look at a natural building stone using optical microscopy, for instance, this would be a typical image that you can get. And here I selected 3 thin sections under using a petrographical microscope to look at them. So 3 limestones from France, Noyon-Fine, Savonnière, and Veerle. And those are all rocks that are also used as building stones in monuments in Belgium and in France, and also in the Netherlands. And so if you would scan them, you would have an image like this. So this is one reconstruction, one slide that you see in the bottom of a CT image. The difference is that in the upper image, first you need to make a thin section, so there is some preparation, and it's destructive. In using CT, you can just put your sample inside the scanner and look at it without any sample preparation. Also, advantage is that with CT, you can see whatever cross-section that you want, or you can look at it in 3D, while this is not the case with optical microscopy on the top, where you look at your sample in 2D. Disadvantage is that with optical microscopy, you can determine the different minerals, which is a challenge when using CT. But I will go more in detail on that as well. So potential workflow could be you first take a bigger sample, you scan it at a medium resolution. Maybe you've also polished the sides, so you can combine this with scanning electron microscopy combined with EGIS in order to get chemical information, and you can then do mapping of or registration of what you see with SEM EGIS combined with CT in order to get a kind of estimate about the composition. You can also combine this with X-ray fluorescence. Or you can do a medium resolution CT scan. You see the zones, then you take subsamples, you go for higher resolution. And if this high resolution is not good enough for in resolution style, you can even take subsamples, combine this with focused ion beam scanning electron microscopy, or coherent small angle scattering, or you can go with your samples to the synchrotron for higher resolution if needed. So often we go for microplugs, and often the examples are also in the articles that we have published. We often take samples in the order of 8 millimeters diameter, something like that, because we think that this is a good balance in order to see the details of our sample and to be able to say also something about the general overview of a process, because this is also important. So here, for instance, if you do a scan and you see different zones, you take subsamples, and this allows you to then start to discriminate the different minerals and the microporosity. But sometimes this is not enough, or often this is not enough. You want to have even more detail, and resolutions in the order of 2.8 micron are not enough. So you combine this then by examining this with scanning electron microscopy, which is of course then in 2D, allows you to get nanometer resolution. If you want to go for 3D at nanometer resolution, often people use focused ion beam scanning electron microscopy, because then we can get the structure in 3D. And if you're not familiar with this, well, the basic principle is that if you have a material with the focused ion beam, you remove some material, you make an opening, and then with the electron beam, you take a scanning electron image, and then with the focused ion beam, you remove some material, you take again an image, and by doing so, you're able to go for a 3D data set. Drawback of this technique, well, it's on a small volume that you're analyzing, and it's destructive. So it's not suitable to do dynamic imaging. If you want to see, okay, for instance, if we were examining in our case clay behavior and the influence if you change relative humidity, this cannot be done with focused ion beam scanning electron microscopy. And so a technique that we use, so if you want to go for high resolution 3D, a possibility is coherent small angle scattering. And so this is also known as psychographic tomography. And this can be done, for instance, at the CESAX beamline at the Paul Schroeder Institute in Willingen in Switzerland. And there they can reach resolutions up to 16 nanometer in 3D non-destructively, also allowing you the possibility to obtain chemical information. And the way it works is that you have the synchrotron and you record overlapping diffraction patterns for many angles, and you scan your material. But there are also some restrictions that you have to keep in mind. For instance, it only works on very small samples. So similar like the volume that you analyze with focused ion beam scanning electron microscopy, also here we are looking at tiny samples. So you have to use often a FIB-SAM just to prepare your sample and to be able to have it ready for your experiment. So here we used a sample of 40 micron, so very tiny. But with this technique, we are able, you can do freezing, you can change temperature, relative humidity, and record the behavior of your material. And so we did this some years ago. And for people who want to know more details about what I'm telling you, most of the things are already published or can be found in Web of Science if you look under my name. So here we took a small sample and we scanned it at a certain relative humidity, and we wanted to see the contact angle inside the pores, which was important because we were focusing also on the effect of the contact angle. And we were very happy because we could see resolutions of 88 nanometer and voxel sizes in this case up to 17 nanometer. And we could distinguish the different materials. We could, so we can quantify the porosity. We can measure, for instance, if you expand this with, we can measure the expansion of clay minerals. So if we change the relative humidity from dry to wet, you can monitor this and measure this. And you also get chemical information. So in our case, by having this done, we could determine that this was the glue that was used to glue our sample on the sample holder. So this was, unfortunate, but also important because it allows us to give information about what we were measuring. But one of the problems is, and that is something that you can see, is that if you want to go for higher and higher detail, we are going for smaller and smaller samples. And there are many studies related to a representative volume element and things like that. But it's a drawback, of course, that you have to have very small samples in order to say something in detail on the resolutions below 1 micron. And so one of the things we are currently doing is trying to explore if there are new techniques or other techniques to try to solve this or to contribute. And currently in our team, we are working on X-ray grating interferometry. X-ray grating ferrometry was already done by Matthias Kajas at Paul Schroeder Institute at the synchrotron, and this was also published in 2017, where he published the work on dual phase grating interferometry for tunable dark field sensitivity. And the idea is that by applying gratings combined with CT, that you can get, besides just the normal absorption image, you also have differential phase contrast, and you also have dark field image. And that by using this technique, you are able to gain information of sub-resolution features. And so we have a collaboration with this, with several partners, and in collaboration with Marco Stampanoni from ETH PSI. And the idea is that if you have a standard CT system where you have a source, sample, and detector, we now apply gratings. And gratings that can change parallel to each other and also perpendicular to each other. And by playing with those gratings, we get different signals in our detector. And so if we play with those gratings while changing their position, we get absorption signal, we get a different phase contrast information, and we get also the dark field signal. And so, yeah, I should move this maybe a bit. I can't. Okay. So yeah, and so by combining these three, we are looking for ways to get information below resolution. And an example which we tested last year was roofing tile, where we know that porosity on average is around 34%. When doing in lab under vacuum water intrusion, we can know the normal porosity of this, open porosity of this material. But we also know that this material has a high amount of pores below 1 micron. And so if we scan this with our Hector scanner, which is one of our scanners, where the samples you see here, this is a sample of several millimeters diameter. Based on what we see as the darker areas, which are the pores, we obtain a porosity value in 3D of around 2%. If we go for a smaller sample, so here it's a sample of around, I think, maximum 1 millimeter diameter, so you can start to question the representativity. But if you take a much smaller sample, we can see much better all the pores. So you see that the amount of pores is higher now, but still we are missing more than half of the pores present. So that is why this kind of material is very difficult to say something or to study using X-ray CT in lab. And so we we went to the synchrotron to test the idea of the grating interferometry. And this is the result. So on the left, you see, we took a sample of 1.5 millimeter and scanned it with absorption and scanned it in the dark field using the gratings. And now what you see, for instance, if you look to the blue circle, here there is a zone where you see it is like a grain. But difference in gray values can be due to a difference in composition, but it can also be that you have, for instance, a microporosity present. This can be important if you want to know if you have a rock which consists of dolomite and calcite and you have difference in gray values, you want to be sure, for instance, that the difference in gray values is due to the fact that you're dealing with dolomite versus calcite and not because your calcite contains, for instance, microporous zones which are below resolution, and because of a partial volume effect, you cannot distinguish them. So in the dark field image, we see that this area is darker, having almost no signal. And this is an indication of no, there are no pores present, and this is a full grain with no microporosity in this area. And by playing with the gratings, we even have the possibility to say there are no grains in the size of, in the order, for instance, between 300 and 600 nanometers. And that is what we want to come in the end, is that we are able to map the different zones and say, yes, there are pores below resolution in the order of this and this diameter. It will not be that you will be able to distinguish the individual pores, but it will allow you to say something about zones and microporosity. Then the next thing is 3D chemical characterization, because besides structure, also chemical characterization is crucial when understanding rock behavior. And so, as I mentioned before, you can combine, for instance, CT with SAM-EDS by co-registration and try to get an idea about the chemical composition. You can combine micro-CT with X-ray fluorescence, because also this is an excellent technique to give you information about the chemical properties which are not able to be detected with X-ray CT. And In the past, we did this, did this by first taking a rock, scanning this with micro-CT. We could distinguish different gray values because of the difference in chemical composition and average atomic number. And then we took the sample to a micro-XRF scanner. We got information about the chemical information. And then by cluster analysis, we could say which kind of minerals they were. And then if we linked the gray values with chemical information from XRF, we could give a kind of estimate about the 3D distribution. But this was an estimate because it was based on gray values that are present combined with prior knowledge. But the fact that combining this was an ideal thing was for us a reason to invest in a new system, which we call our Heracles scanner, where we have a CT system which combines two XRF end stations. So now there is no manual need of going from one system to the other, trying to register those data as well. But now we can first do a CT scan. So here you see the CT system. This is the source. Here you have one of the detectors available for X-ray detection. And then we have two end stations, one for XRF tomography and one for confocal XRF. And depending on which end station you use, you have different resolution. In the confocal, we have a focal spot of 10 micron. In the XRF tomography, a spot size of 20 micron. But now what we can do is first we can do a scan. We can say, okay, I'm interested, for instance, in this point. I want to have the analysis of this point. So this allows us then to move to one of the end stations and, for instance, take the spectrum out of that region. You can also draw a line on your radiograph and get a mapping of a line profile of the chemical composition. Another thing is it allows us also to do a kind of micro XRF tomography. But honestly, for rock material, this is very challenging because XRF signal is only penetrating up to 200-300 micron. And it's also depending on what you're looking at. So for instance, if you're looking at a light material, which consists of one gold particle inside, it will be easier than if you're looking to a rock with gold particles inside. But I wanted to test the sensitivity, and I took a limestone with gold nanoparticles and wanted to see if the system could detect this, because the gold nanoparticles were in the order between 30 and 60 nanometers diameter. And here you can see that it was very sensitive for the gold, which is shown in green. But you can also see that in the middle, we are, of course, missing information because XRF gives only information about the surface area. So we are also exploring on new methods in getting more chemical information of our rocks. And one of the ways we are working to solve this is by using hyperspectral detectors. So this is called in literature hyperspectral X-ray computed tomography or color X-ray CT. The difference is if you have your standard setup, you also have your source, your sample, but now you use a hyperspectral or a multispectral detector, which is able to register the signal, which can provide you chemical information. This was already published in 2015, the idea, and we are working on this currently in our lab to apply this for instance, for ore characterization. So we have different hyperspectral detectors, like DSLCOM is sensitive for low energy, Hexitech is more sensitive for high energy. And so if you now have a sample, which is a mixture of quartz, tungsten, gold, and lead, and you scan this with normal CT, you will be able to, you see here the radiograph and a reconstruction, you will see bright spots which are linked to, can be lead, can be gold, can be tungsten, but we don't know. We don't know with just this information which grain we are looking at. And if we scan the same setup with the hyperspectral detector, we can also distinguish those grains. You see that the image is not so high in quality. It's because the number of pixels is lower in a spectral detector compared to a normal CT detector. So the quality is a bit lower, but it allows us still to detect and to see which grains we are seeing in the normal CT and with spectral CT. And based on the spectral information, we are now able to say, okay, this is the tungsten in orange, in red it is the lead, and in green it's the gold. And so we are now working on this to make this better working and more precise. But and this is also in the framework of a PhD in collaboration with the partners mentioned here below on this slide. So this is work which is ongoing. But then you now have the possibility to characterize your rock multi-scale 3D chemical, but then we want to go for fast 4D to see the processes inside our material. So if you want to look at dynamic processes, you need to have sufficient time resolution. And typically what is done is people for fast scanning, they go to the synchrotrons, because typically with micro CT, you often have a scan like 20 minutes is really realistic. And because at synchrotrons you have a much higher flux, you get much faster signal, you can do very fast CT experiments using synchrotron. And so you can even reach like 208 tomographies per second. And I've showed here a map of where you have all these kind of synchrotrons available spread over the world. So this is what is typically done. Because the access of this kind of systems, synchrotron systems, is depending on the availability and if you have given beam time. We developed already in the past a dynamic CT scanner. So a system where we could do dynamic imaging, where we had continuous scanning in around 20 minutes. And where we are looking at dynamic processes. And now we have a system where the source and detector are rotating, and this was because we wanted, if you want to control dynamic processes, you want to have sensors in temperature, you have flow lines connected to your sample, then it's sometimes easier if this is stable than if this has to rotate for 20 minutes continuously in a fast way. So we have selected a scanner, we built a scanner where the sample and the entire setup of our sample is stable. And so if we then, we also invest in different add-on modules for in situ imaging. So to do reactive fluid flow measurements, to mimic a difference in climate, temperature, relative humidity, to do freezing experiments. We have also a system, a Deben system for compressive and tensile testing, where we can combine it with capillary water uptake and temperature control. And this allows us then to, for instance, examine solute transport. So I want to mention here that here indeed the sample size is small. This is a rock or Savonnière limestone, now fully saturated with water, and we are injecting in function of time a cesium chloride, and we want to monitor how this is spreading. So we want to look at, we want to see how this transport is of cesium chloride is spreading inside the rock by advection and diffusion. And so as you can see, we are scanning very fast, and you can follow really in function of time which pores are being slowly filled with the cesium chloride. So the cesium chloride is from the bottom and then moving through the sample. And you see how the concentration in cesium chloride is changing in function of time. So this is done in lab, and this allows us to already have an idea about dynamic processes. If this time resolution is not high enough, we also submit proposals to go to the synchrotron, or we use this technology also to prepare our experiments at the synchrotron. So Besides looking at the process, we can also say something about the relative concentration in function of time in each individual pore. So what you see here, for instance, is if you virtually divide your open pore system into individual pore bodies and pore throats, you can then say, okay, this pore volume, when did the salts, the cesium chloride entered, what was the time, what was the concentration, so you can quantify this, which is very powerful. Besides just looking at how it is moving, you also want to know, for instance, how salt is crystallizing. So you can look at individual salt crystallization. So this on the upper left, you see salt crystallizing out, so scanned in real time. And here you see a sample, a sandstone sample, which is saturated with the salt solution in green. And then you see that it gradually is drying out. And in red, so artificially we color coded this, you see how where the salt is precipitating. And because it's a non-destructive technique, we can monitor, okay, if we now re-wet our sample, what will happen, and if we dry again. And so if you can, so now you have the possibility to do cycles of changing humidity, temperature. And this allows us to see, for instance, that if you re-wet and dry again, that the salt is not precipitating at the same location, but it starts to migrate inside your material, which is totally logic, but it's important input for models that are modeling, for instance, salt crystallization, and it's a good validation tool for that. So if you have a CT scan, you can also extract the individual pores and using pore network extraction, for instance, by using the procedure which was already published in 2009 by Hugh Dong and Martin Blunt. But so you are able to extract those. You are able to say something about pore size distribution. You know each individual pore, you know each individual pore throat. And then you also have the possibility, if you do dynamic imaging, for instance, to say, okay, I have here my yellow pore. I want to follow in function of time how the gray values inside this pore are changing. And if it was originally filled with a salt solution with a certain gray value, then two things can happen when you dry it out. Or it can dry out and it becomes empty, so it becomes filled with air and the gray value will become darker for air, or the salt crystallizes out in this pore. You get so you get a denser zone and you get brighter areas, and so you can do this for each individual pore and each individual pore throat or each individual location. And this allows you to say something about, okay, which pores at which dimension and at which time start to be dried out and not being filled with salts, and which are being filled with salts. So you can get really quantified information and detailed information based on your experiments. So with CT, you can study salt ice crystallization. We use this to study freeze-thaw cycles. We use CT for reactive fluid flow to check the effect of an acidic environment. We use it in our team for microbiological activity to see, for instance, here you see calcite precipitation artificially colored in yellow due to bacterial activity, to see which fractures or which pores are being filled due to microbiological activity. We study fracture behavior, so we can monitor the link between the original structure and the fractures. And we can do fluid flow experiments, as mentioned already. And use this information, for instance, to say something about conservation of cultural heritage, but also something for reservoir rocks, for instance. But the challenge is now, we have now all these possibilities, but how do we put this information into explaining or predicting what's happening in a sample of several centimeters, and in the end something in reservoir scale or a building in reality. And so one of the things is that CT can be used as an input for pore network models. I'm not a modeler, I'm more the experimentalist, but CT is important because it allows you to extract, for instance, the different pores and the pore throats extracted from micro CT. You can combine information of porosity that you have obtained with the different techniques at higher resolution and put this into one multi-scale pore network model, and then use this to, for instance, model behavior like water being displaced by a non-wetting phase. But you can also validate this by using dynamic imaging. And so what you see on the left is modeled and on this stone, and on the right you see how oil is displacing water in the same sandstone in function of time, where we made the, so I will repeat again, so where you see that oil is coming from the right to the left, also similar like in the model, and the model is based on the CT information here, and so you can start to validate those models. And this brings me to the end, that I want to say that now a lot is possible related to imaging, both in lab environment as well as at synchrotrons. A lot, I've only touched a few of the possibilities that can be done, but follow this closely. This goes very fast and there are many things that are possible. Combine this information also with experiments that you do in lab. For instance, I have access to the labs also in Utrecht, and if you combine and make complementary data, this is really important because it provides you better insights. And then if you can combine this advanced imaging experiments with modeling, it's very important, but also to validate what is modeled with the imaging is also a very important aspect. But this also requires an interdisciplinary approach, and this is also, I think, where I really strongly believe in, is that you have people who are very strong in experimental approach and the modelers, and it's by combining those different two different aspects that you can really come to better insights. And I think if we continue the way we are currently doing, that at a certain moment we will be able to model what's happening on the lab scale and in the field scale in an even more precise way than what we can currently do. And so hopefully I would invite you to visit our city center to see how the monuments look like, or if you're interested in our cultural heritage, for instance, and their weathering behavior. But maybe in the future this will be possible. And this brings me to just what I want to say. What I want to mention is that last week I got good news that our proposal for integrating research infrastructure in Europe was approved by the Horizon 2020 call for Infraia. And so our project X-Site, where we combine electron and X-ray microscopy communities for structural and chemical imaging techniques on Earth materials, which will mean that over Europe, including the UK, we have around 15 facilities that join. And once we are running, I will keep you posted with that. Once we are running, people will have the possibility to ask for beam time in my lab, for instance, or in Utrecht, or in another lab who is partner in this project, and can get, if so similar like at the synchrotron, that they can get access to it if the proposal is well, and then all the costs, the scanning cost, the travel cost, or sending the samples is covered by this project. So this is maybe also a possibility for you to have access to the infrastructure I showed you. So I want to thank you all for your interest. I also want to thank the past and the current UGCT members, as what I was showing was, of course, also the work of a team and not myself alone. I want to thank you and maybe just bring it to the attention that for next year there is also a Kimberly-Clark Distinguished Lectureship Award given, and so you can also invite this professor. Thank you very much, and now I will stop sharing my screen. Voila. Yes.
Excellent. Very exciting presentation, nice examples, really nice. Really, thank you very much. So I will just start with some questions that started appearing in the chat. So so Kamal Sain is asking whether you have used laser ablation methods for preparing samples, for example, for ptychography.
No, we haven't used laser ablation. The last time we did was we used focused ion beam, and well, we did this, but the problem was it seemed to be very difficult to prepare our sample because there were different fields. The clay area was very soft, and then the minerals were very hard. It took a long time for them to be almost ready for the synchrotron, and then in the last moment they suddenly had to mail me that they lost the sample in the vacuum. And so in the end what we had to do is just take some grains, crush them, and manually select them under the microscope. Yeah, so this was a real so the sample preparation was a real challenge here. Yes. Great.
So Luis Albornoz Para, I hope I pronounced correctly the name, says, fascinating insights provided by the new technology you are developing. This talk has been very interesting to me, someone who loves building stones conservation. Great. It also shows me how much things have moved on since the days I started 25 years ago. I would love to subject all UK building stones to your test. Thank you. I shall check for published information you have mentioned.
Yes, I think we'll become very good friends. Yes, I also have a passion for stones and cultural heritage and rock. So yes, we should get in touch.
Great. So other people, Omid said that this is fantastic talk. Boris Musafa, very interesting talk. So a question for Puyan. Any estimated time frame for the EXITE opportunity? So when we'll start?
Yes. So we now just got the news by Europe. So this means we are now starting all administrative things. Then the next step will be to start hiring a person. So my university told me I can open the vacancies from probably next year, but people also have to have a visa maybe to enter the country. So we expect or hope to start the project somewhere around May 2021, and then in the project we first take 1 year of setting up the entire infrastructure with all the partners, the way to check all the proposals, things like that. And then so I estimate that somewhere May 22 first scans will be done, and then it is continuously for 2 years available. So I would say somewhere like September, October next year, probably I would assume that maybe proposals can be submitted so that we can really start somewhere. So that is what my estimate. But then it is 2 years fully available. So there I will also specifically hire a person who will be your contact person when doing experiments. And so, well, now this is done by my current postdocs and PhD students.
Yeah, it makes sense. Great. I have a couple of more questions not posted in the chat. These are my questions. And these are relatively open questions, I would say, but I would like to get your feedback. The one is related to the representative elementary volume and the sample of the size, because you have very nicely mentioned that the samples have to be small enough in order to gain a great resolution. So how should we deal with heterogeneities within the samples? Because either we focus on building stones or on subsurface materials or even composite materials. These materials might contain heterogeneities inside, which might differentiate the flow patterns or the deformation actually. So how representative our results can be for the understanding of a material from a material science point of view, you think?
Well, the way I approach it is to look for which question do I have. And for instance, if I want to know, okay, if I inject this, or if I do this, or I change the temperature, or I change the water saturation, I will try to understand the process itself and not say, okay, give me a sample of 10 by 10 centimeters and I will tell you all about this. So at the moment, I'm more in trying to understand individual processes in order to gain a better insight in the behavior and in order to use this as input for models. Then that we are able now to say, okay, by having this analyzed, I can say something for the entire quarry. And so my approach is in this point maybe a bit different. Of course, also we in Belgium, we are all funded often, it's for fundamental research most of the times. We are not, we have collaborations with industry, but we often work on a methodological point of view than in having the entire answer ready as you probably want to have or hear. So our approach is that, well, we start with samples which are big, like what people also do using, the cores of 10 centimeters. And then what we do is sometimes if we don't, if we want to look for fluid patterns, we use then maybe sometimes tracer elements. So tracers in order to highlight the zones that are maybe not so visible individually. But then by doing scans before and after, we are able to see, okay, in a bigger, lower resolution, this is the info that we have. But if we want to know, okay, what is the fact of the impact, for instance, on the microstructure on the fluid flow, then we will go for smaller samples in order to answer this and try to use this information to get the bigger picture.
Great. So it's more like an approach that concentrates on the structure of the sample that you're investigating to extract the processes and the better understanding, rather than expanding to the whole material and generalize, which is really great, I think, in terms of experimental mechanics. Okay, so my second question, and this is again kind of general, you mentioned at the very beginning very nicely the lab and reality and how different they can be. And usually experimentalists try to understand processes in the lab, especially with the advanced experimental methods. But you pointed out a difference, saying that sometimes the conditions that apply to the case study, to the nature, to the outcrop or the building stone are not the same compared to those we try to reproduce in the lab. And I understand this because we have to simplify, to make as simple as possible our understanding first and then combine it. Do you think that we will be able at a day to observe in the lab more complex processes that combine more than one parameters? Yeah. Or do you think that it's always better to try and deconstruct, if you like, the whole thing and say, okay, now I'm focusing on the weathering, now I'm focusing on the loading, now I'm focusing...
No. So my ultimate aim is to combine as much as we can. And this is also not by just doing CT or combining CT with advanced flow cells, but is also by combining different techniques like acoustic measurements or measuring certain signals, like because we can observe, for instance, because of difference in temperature or difference in sound, that something happened inside, which we then combine with the images and help us to detect what is happening. So I think that there is still a lot that can be done, and also that I think we need to also invest in going from, if you have the radiographs with the CT scanner, for instance, you have all these steps, and in all these steps that you do, a lot can be done wrong also by the user itself. And it would be good that, based on just the raw data and the signals from the different instruments, from temperature sensors, that you can derive to an automatic information that you obtain. So I think, and that is where people are currently working on, I think. I think we still, and that's also, if you look in literature, there are so many things that are currently being done, both in lab, both in synchrotron, both on the reconstruction algorithms, on the data analysis, on combining techniques, that I think this goes so fast. I really believe that in the next 5 to 10 years, still this will evolve a lot. So I really see there still a lot of potential evolvement. Yeah.
Great. So no more questions from my side. Do you have an? Yes, Ellen Lewis, many thanks. It was really helpful to see how different characteristics can be addressed together, both advantages and disadvantages. Okay, yes, people are started leaving slowly because we have exceeded the time. So I would like to bring this to an end, and thank you very much, Veerle, for joining us this afternoon. On behalf of IG and Heriot-Watt University, I would also like to thank the InterPore and the Kimberly-Clark that gave us the possibility to host you today. Great talk. Thank you very, very much for joining us this afternoon. Thank you.
It was a pleasure. And anybody can always mail me if they need more information.
Great. And thanks everybody who has joined our discussion this afternoon. Thanks. Bye.
Bye. Thank you.